Good afternoon, Ashok sir.
Good afternoon, Xavier sir.
Okay,
Good
yes,
afternoon.
good afternoon. Okay, good afternoon, Shafi sir. Okay, good afternoon, Shafi sir.
Recording.
Okay. Vibration. Sir, principal ഇപ്പോൾ join ചെയ്യുന്നതാണ് sir. ഇപ്പോൾ അശോക് sir. Okay sir. Okay. Okay. Shafi sir, good afternoon.
Good afternoon, sir. Good afternoon.
Okay.
Sir,
So I think Gigi sir has also joined. So let us start, Ashok sir. Ashok sir, can we?
Yeah, you can start if everybody is there. That's no
Okay.
issue.
Okay then, sir. So today we are having the open defense of Ms. Sheena Latif. She is a research scholar with the Electrical Department, College of Engineering, Trivandrum. Dr. Ashok S., a professor in electrical engineering, NIT Calicut, is the chairman of Board of Adjudicators. I welcome you, sir. I extend a welcome to Dr. Shafi K.A., Dean, Faculty of Engineering and Technology, University of Kerala, Dr. Gigi C.V., Principal, College of Engineering, Trivandrum, and all faculty and researchers for this open defense. Over to Ashok, sir. Ashok, sir.
She can start the presentation.
Okay, sir.
okay, sir. Thank you, sir. Respected teachers and my dear friends, a warm welcome to the open defense.
Excuse me, Sheena.
Yes,
Dr. Xavier, can you start recording?
Sir, mute.
Dr. Xavier, can you please start recording?
Yes, teacher. Yes, teacher.
Yeah. Sheena, sorry.
Thank you.
Please go ahead.
A warm welcome to the open defense of my thesis titled Investigation and Analysis of LVRT Schemes in DFIG. I'm Sheena Latif, doing full-time research in the Department of Electrical Engineering, College of Engineering, Trivandrum, under the guidance of Dr. J. Xavier, H.O.D. and Professor, Department of Triple. These are the table of contents. Introduction, low voltage ride-through. Low voltage ride-through is a grid code requirement which demands the wind power generators to remain connected to the grid and to withstand a voltage dip for a specified duration of time without disconnection. As evident from the LVRT characteristics of various grid codes, different countries have different minimum LVRT voltages to be withstood, and also the time duration for which they should remain connected without tripping is varying according to the different countries' LVRT grid code requirements. Literature survey on the LVRT technologies in DFIGs revealed that the LVRT solutions for DFIGs can be broadly classified into hardware solutions and software solutions. The hardware solutions basically includes the implementation of fax-based devices such as STATCOMs or DDRs, or the implementation of crowbar technologies. While as the software solutions include the modification in the control strategies of the RSC or GSC of DFIG, such as modified vector control, dual sequence control mode, etc. So our research concentrates on the severe fault condition where there is a requirement of fault current limiting during LVRT in DFIG. And the literature survey shows that the initial works were basically concentrated on severe symmetrical voltage dip conditions, where overcurrent limiting was performed using crowbar switches or other resistor type hardwares. Later on, a partial voltage dip condition was considered for voltage restoration using a dynamic voltage restorer. Afterwards, partial and severe unsymmetrical fault conditions were also considered. And mostly it were the hardware solutions such as switch type resistor FCL, inductances, rotor side inductors, or superconducting fault current limiters, which were implemented for overcurrent limiting. In most of the papers, overcurrent limiting was possible, but the applicability, the reduction of harmonics component in the rotor current was either not considered or not discussed. So as a research gap, we can say the software solutions which are suggested for normal LVRT in DFIG depends on the modification in the control strategies of RSCs and GSCs, which is applicable only for partial voltage dip conditions. For severe voltage dip and fault current mitigation, hardware solutions becomes a must. And all hardware FCL methods are not equally applicable for both severe symmetrical and unsymmetrical fault-based overcurrent reduction. Symmetrical and unsymmetrical faults have different impacts on the rotor currents of DFIGs. A dynamic voltage restorer can deal with symmetrical and unsymmetrical partial voltage unbalances with equal efficiency. So as an objective of our research, a single FCL-based LVRT solution is investigated for, which can reduce the overcurrent during transient as well as steady state, during severe symmetrical and asymmetrical fault conditions, and which can also avail voltage restoration during partial voltage dip conditions. Therefore, the fault current limiting property of the DVR is investigated for protecting the RSC of DFIG. What is a dynamic voltage restorer? A dynamic voltage restorer is a series compensated custom power fax-based device usually installed in the distribution side of the power system. Here is a DVR installed between, the figure shows a DVR connected between the grid and the DFIG. It consists of a DC source, a voltage source converter, a low pass filter, and a series injection transformer. The statistics of DVR as an LVRT solution in DFIG shows that the interest of researchers with the DVR as an LVRT solution has gradually increased from 7% to 36% from 2009. The analysis of the various proposed control strategies of FCL and DFIG is carried out in MATLAB simulation environment. In the first phase, rotor overcurrent reduction by phase-shifted dynamic voltage restorer, that is a stator voltage control technique, is investigated. In the second phase, this PSDVR method is combined with a software technique of virtual impedance-based RSC control. To overcome the drawbacks of this phase, a dual-controlled RSC with PSDVR for unsymmetrical faults is also proposed. And in the final phase, stator impedance improved overcurrent reduction in the stator and rotor of DFIG is investigated. So overcurrent reduction using phase-shifted dynamic voltage restorer. Throughout our study, throughout this research, small p represents the voltage dip ratio given by pre-dip voltage minus post-dip voltage by pre-dip voltage. And during unsymmetrical voltage dip conditions, negative sequence component in the stator voltage is represented as small q or Vs minus. In this phase, the fault parameters that we have considered is a double line to ground fault and a severe symmetrical fault with a p equal to 0.8. During a fault period, we can see two periods occurring during the fault period. Immediately after the fault occurrence and the fault clearance, it is the transient period, and between two transient period is the steady state period. The DFIG for analysis is modeled in stator reference frame based upon the fundamental equations of stator voltage, rotor voltage, and stator and rotor flux, and the equivalent circuit of the DFIG obtained is shown. The single line diagram of the DFIG that we have considered for simulation and analysis, that is a 575 volt 60 hertz DFIG connected to 22 kV grid, is also shown, and the DFIG parameters for simulation are represented in the table. Dynamic behavior of a DFIG during severe faults. During severe symmetrical voltage dip conditions, the transient and steady state overcurrent occurs in the stator as well as rotor. Whereas in the unsymmetrical voltage dip condition, together with the transient and steady state overcurrent, there will be a negative sequence component present in the rotor currents. For the operating slip of S is equal to minus 0.2, it is the 11th order harmonics that occurs in the rotor current during unsymmetrical voltage dip conditions. And unsymmetrical voltage dip conditions, we can see another factor, voltage unbalance factor, given by Vs minus by Vs plus. Dynamic equations of DFIG during symmetrical fault conditions. If T0 is the instant at which fault occurs, then the stator voltage magnitude now reduces to 1 minus P into V1 if it is a phasor which is rotating at a synchronous speed. In the case of a stator flux, in addition to the steady state component or the forced component of the stator flux, an additional component of natural flux also occurs in order to avoid any discontinuity between the pre-dip and post-dip conditions. And this component, the homogeneous or natural component, is an exponential decaying component, and it is directly proportional to the depth of the voltage dip conditions. Corresponding to psi SF, corresponding to these natural and forced components, there will be rotor force and rotor natural components occurring in the rotor. During unsymmetrical fault conditions, the stator voltage, stator flux, and natural flux components will have both positive and negative sequence components. In the rotor force, total rotor voltage, if we see, the negative sequence rotor forced component is having a magnitude 2 minus s into q, which is rotating in the opposite direction with the frequency 2 minus s into omega s. This will cause serious problems for the DFIG in the case of supersynchronous mode of operation. So a phase shifted dynamic voltage restorer. A novel strategy of DVR compensation is developed to decrease the transient and forced components of the rotor currents. In this strategy, the transient period is controlled using DVR mode, the steady state period is controlled using PS-DVR mode, and phase angle correction is also taking place during DVR and PS-DVR action. The PS-DVR control algorithm and the parameter determination using the equations are shown. So as soon as a voltage sag is detected, the stator current is checked for any overcurrent. If there is any overcurrent detected, the PS-DVR will activate the DVR mode of voltage restoration for the initial 20 to 40 milliseconds, after which a steady state period happens and the PS-DVR mode will be activated for steady state fault current limiting. This continues until the rotor current is regulated to the rated value. Even after the rotor current regulation, if there is any voltage dip occurring in the stator, that can be controlled using a DVR action. The parameters determined for the PS-DVR is given in table 4. So phase shifted DVR compensation is the modes of PS-DVR is explained using the voltage phase diagram. The figure A shows the partial voltage dip compensation usually done by the DVR mode, where theta 1 is the phase angle jump. The sag voltage is lesser in magnitude compared to pre-sag voltage, which is compensated in both magnitude as well as phase angle by an angle of injection theta by the VDVR. Now coming to the PS-DVR mode that we have proposed, figure B shows the transient mode and figure C shows the steady state mode of action of our PS-DVR. During transient mode, the same DVR mode is activated, but since the stator voltage is severely low, the stator voltage has fallen to severely low condition, it is not able to compensate the voltage to its pre-sag value, but the phase angle correction takes place. Whereas afterwards, after the transient mode, it is a steady state mode in which the transient voltage is injected with a voltage VPS-DVR in opposite direction such that a steady state voltage VSS is obtained, which is less than VSAG in magnitude, but phase angle correction takes place. The PS-DVR control strategy with the PR controller, proportional resonant controller for LVRT and DFIG is shown for transient and the steady state compensation. In the transient period of DVR strategy, both positive and negative sequence components are controlled by comparing the reference values with the measured values in the alpha beta reference frame, and the error is controlled using proportional resonant controller. Proportional resonant controller transfer function is given in equation 19. The output of the error is fed to the 6-pulse generator of the DVR. During PS-DVR mode, the positive sequence component reference value now changes to LVRT minimum voltage, and the negative sequence component is regulated to 0. The errors are controlled using PR controller, and the output of the controller is fed to the pulse generator of the PS-DVR. The PS-DVR mode of action for a symmetrical fault of P equal to 0.8, the DVR mode of action for a symmetrical fault of P equal to 0.8 and a double line to ground fault is shown during transient period. During symmetrical fault, we can see the phase angle jump is reduced from 70 degrees to 5 degrees with a voltage increment. While as in the case of double line to ground fault, the phase angle jump of 86 degrees is reduced to 32 degrees in the B phase, and C phase is regulated to in phase condition with a voltage increment and phase angle correction. The double line to ground fault steady state action of the PS-DVR is shown here. Here the value of the stator voltage is decremented. So it is a voltage decrement mode. The stator voltage values reduces to 122 volt while the phase angle correction is still continued. So based upon this PS-DVR action, the rotor current regulated for a double line to ground fault is shown. We can see that in the transient period, there is significant reduction in the peak values of the rotor current. While coming to the steady state period, the peak value of 2 per unit is regulated to 1.8 per unit only. The proposed method is compared with an enhanced field-oriented control with the supercapacitor method. And we can see that the transient component reduction in the rotor current is comparable with our method is comparable with the existing topology, while it's a steady state rotor current reduction in our method is not significant. And also, but in our case, the harmonics component has been reduced, and negative sequence stator voltage component is also reduced. So as the advantages of this proposed method, the RSC control sustained during PSDVR action, natural flux and steady state components are controlled separately, and it is applicable to symmetrical and asymmetrical voltage dip conditions with the phase angle correction. But it has severe limitations. That is, the steady state voltage reduction method is not applicable for voltage dips closer to LVRT minimum voltage, and limited rotor current harmonics reduction, and the reduced steady state rotor current is above the stipulated safe limit. These are the publications of this phase. So in order to overcome the drawbacks of the PSDVR method, a virtual impedance RSC control method is suggested in the next phase. The virtual impedance RSC method was initially suggested in the symmetrical grid voltage swell condition as a transient flux reduction method. And this method we have adopted for the LVRT and also the steady state period due to the simplicity of RC control and the absence of external resistances or inductances. The faults considered here are the previous faults itself, double line to ground fault and a symmetrical fault. So the virtual impedance method actually envisages the addition of rotor inductance and rotor resistance virtually to the existing rotor circuit of a DFIG. From the rotor forced and the rotor natural current equations, we can see that the rotor current is inversely proportional to the rotor impedance. Therefore, the addition of rotor virtual inductance and resistance can reduce the rotor forced and natural current components. KT into RA and KT into LA are the virtual resistances and inductances which are added to the actual rotor circuit of a DFIG given in the rotor equivalent circuit. This is equivalent to, in the inner current control loop of the RSC, this is equivalent to adding a negative closed feedback loop with a gain RA plus SLE. So the open loop transfer function G of S now changes to G double dash of S. Because of the open circuited rotor voltage, the disturbance transfer function IR by VR0 is determined, and the effect, this step response of this disturbance transfer function is plotted for different control strategies without any virtual impedance, with the virtual resistance, and with the virtual impedance. We can see that the transient component of the rotor current is getting reduced by virtual resistance and virtual inductance method, virtual impedance method, while as in the steady state period, it is the virtual resistance method which has significant contribution in the steady state rotor current reduction. So based on the virtual impedance and the PSDVR combined method, a symmetrical fault condition, the rotor current is considered. The rotor overcurrent is now reduced from 3 per unit and 2 per unit in peak values to 2.26 and 1.9 with the proposed combined control of virtual impedance and PSDVR methods. The forced rotor current and natural rotor current graphical representation also shows that the forced rotor current is reduced from 0.396 to 0.29 during the symmetrical fault, and natural rotor current is also reduced from 1.639 to 1.325. The proposed method for a symmetrical fault condition is compared with an existing topology of indirect matrix converter and crowbar, and the transient component reduced in the rotor current by our method is comparable to the existing topology. The steady state component reduction is also almost equivalent, while as they require a crowbar activation, we do not require a crowbar activation, and also a faster settling time is achieved. Now, the same method of virtual impedance RSC control strategy is applied for an asymmetrical voltage dip condition for a double line to ground fault. And the rotor transient and steady state currents during double line to ground fault without and with the virtual impedance is shown. And we can see that the transient period, the virtual impedance method has its own contribution in reducing the transient peak current values of rotor current, while as coming to the steady state period, the virtual impedance control strategy does not have much impact on the steady state rotor current reduction or its harmonics. A graphical representation of natural rotor current and forced current reduced by different methods are plotted, and it shows that the natural current is getting reduced by the virtual impedance control strategy from 2.07 to 1.46, the combined effect of PSDVR and virtual impedance control strategy, while as in the forced current, it is the PSDVR action still sustaining, whereas the virtual impedance does not have a serious contribution. So, as a conclusion of the phase 2, the proposed method of virtual impedance and PSDVR method can be effective for transient and steady state rotor current component reduction during symmetrical faults. But coming to asymmetrical voltage dip conditions, it is effective only during transient rotor current component reduction. The harmonics reduction as well as the negative sequence component reduction is not significant. It is the Ph.D. reaction which is still continuing. These are the publications of this phase. So in order to overcome the drawbacks of virtual impedance-based PSTVR method, a dual-controlled RSC accompanied PSTVR method is analyzed in the third phase. The harmonics component which is present in the rotor current is mainly contributed by the negative sequence component occurring in the rotor current. So in the RSC dual control strategy, we are aiming at reducing the negative sequence component of the rotor current. In the conventional FOC method, a negative sequence rotor current control or its reference is not available. So a contribution of PSTVR with the dual controlled RSC method is also analyzed. Theoretically, we can say the worst condition that can occur with a VUF, voltage unbalance factor, during a double line to ground fault is 100%, while that contributed by a single line to ground fault in the worst condition VUF can be 50%. And also studies shows that among the asymmetrical fault conditions, it is the double line to ground fault or double line faults which causes serious unbalances in the rotor of DFIG. The stator and rotor currents in the positive and negative sequence are represented. The stator active power, stator reactive power, and electromagnetic torque expressions are also given in terms of positive and negative sequence stator components, voltage and current. We can see that the stator active, reactive power, and electromagnetic torque are having twice the grid frequency ripples contributed by the negative sequence components of the stator current as well as stator voltage. So in order to analyze the dual controlled RSC method, the DFIG sequence model is developed in the DQ axis in the positive and negative sequence components, stator voltage, stator and rotor fluxes, etc. From the power equation, the constant power terms are extracted and the power matrix is generated, where X can be stator or rotor components. Corresponding stator and rotor voltages can be supplied. From this power matrix, the rotor current positive sequence references are calculated to be supplied for the RSC dual control strategy, while as elimination of the or reduction of the ripples of the electromagnetic torque of DFIG is considered for the calculation of negative sequence rotor current references. So based upon these equations, from stator voltage in D and Q axis positive and negative sequence, stator flux, and the power equations, the rotor references in the D and Q axis for positive and negative sequences are calculated and measured, and the error is compared using PI controllers. The PI controller output is fed with two feed-forward terms, which actually represents the natural component of the rotor voltages. And the output is fed to the PWM pulse generator of the RSC. The parameters of fault which are analyzed for this phase is a single line to ground fault which produces a VUF is equal to 50%, a double line to ground fault which produces a VUF is equal to 80%, and a double line to ground fault which produces a VUF is equal to 90%. So coming to VUF 50% condition, the results are compared for the FOC of RSC and the dual controlled RSC. In the electromagnetic torque and the rotor current expression waveforms, we can see that the ripples are significantly reduced in the electromagnetic torque, and the rotor currents are also well regulated to 1 per unit value, while as the harmonic reduction also takes place. The negative sequence active and reactive power components are regulated to 0, and the harmonics component is getting reduced from 0.45 to 0.2. Now for VUF is equal to 80%, again the RSC dual control strategy is analyzed with the conventional FOC method, and the negative sequence rotor current in the D and Q axis are plotted. So the ripples in the D axis currents are slightly increasing, and the negative sequence component is not able to track the reference value. The electromagnetic torque ripples are reduced, and the harmonics component is getting reduced from 0.51 to 0.44. So there is some contribution of the RSC dual control taking place for this VUF. Now increasing the VUF to 90%, we can see the stator voltage in the C phase is dipping to 0 condition. During this stator voltage condition, actually the LVRT minimum voltage of C phase is not satisfied, but still for analysis purpose, this case is considered as a hypothetical condition in order to understand the behavior of RSC dual control strategy. And the control shows that the negative sequence rotor current and the negative sequence Q axis and D axis rotor currents, the ripples are actually increasing rather than decreasing. Electromagnetic torque ripples are also not regulated, and the harmonics component increases from 0.48 to 0.51. So harmonics component is actually increasing, which is a negative result. So we can see that VUF, as VUF gets higher, the dual controlled RSC will be reaching to its saturation condition. While VUF less than or equal to 50%, the RSC dual control strategy is capable of regulating the negative sequence rotor current components. Now, the impact of the PSDVR method with the RSC dual control strategy for VOF is equal to 80% and 90% are considered. Because VOF is equal to 50%, RSC dual control was capable of regulating by itself. Therefore, VOF is equal to 80%, the PSDVR method is applied. The voltage increment mode and voltage decrement mode is shown. And we can see that the VOF stator voltage reduces to 64% by the DVR action, and during steady state period to 71.4% by the action of the PSDVR. The PSDVR supported RSC dual control strategy is able to reduce the rotor current magnitude, and the harmonics components getting reduced also from 0.44 to 0.38. The combined method of PSDVR and RSC dual control strategy, the negative sequence rotor forced component is reduced, negative sequence rotor forced current is reduced to 0.55, and natural component of the rotor current is getting reduced to 1.7 per unit. Considering the third case, which is VOF is equal to 90%. As we have seen, one of the phases have already dropped to almost zero voltage condition, and here we cannot apply the PSDVR method of voltage decrement during the steady state condition. Hence, and also since the LVRT condition will not be satisfied, probably the RSC will be tripping. So in order to avail the ride through of RSC as well as DFIG during this case, that is VOF is equal to 90%, the DVR mode is sustained during the steady state period as well as transient period, and the resultant stator voltage after DVR mode of action is shown here. And the harmonics component reduction by the DVR and RSC dual control strategy is reduced to 0.48 from 0.51 only, while as the rotor current magnitude is getting reduced, there is no significant reduction in the harmonics component by the DVR strategy. Because we have increased the rotor voltage, the rotor forced component is increasing to 0.116, while as negative sequence rotor force component is slightly reduced by the RSC dual control strategy. And natural component of rotor current is also reducing. The proposed PSDVR aided RSC dual control strategy for a double line to ground fault is combined with a conventional crowbar method, and we can see the transient component rotor current reduction is almost comparable with the crowbar method, and steady state rotor current reduction is also similar to crowbar method, while we do not need a RSC deactivation during this period. So as a conclusion of this phase, RSC dual control strategy is effective in negative sequence rotor current control if it is not reaching its saturation condition, and PSDVR or DVR has a significant role in reducing the VUF and assisting RSC sequence control. But as the limitations, severe harmonics are present in the rotor current when voltage dip is severe, and there is still room for mitigation of harmonics content as VUF is getting higher. This is the publications of this phase. So as in the final phase, we are suggesting an improvement in the stator impedance as well as the stator voltage by utilizing the filter impedance of the DVR. This is named as FCL DVR impedance method. The FCL property of the DVR for DVR filter impedance is investigated in order to reduce the rotor current harmonics, in order to avail partial and severe voltage, partial as well as severe voltage dip restoration, stator voltage restoration, and also reduction of stator and rotor overcurrents in transient and steady states. In the FCL DVR impedance method, as we can see, it is a DVR itself which is connected between the grid and the DFIG stator. The only difference is we have two anti-parallel switches which are connected across the between the VSC and the filters. These anti-parallel switches will be triggered as soon as a severe fault current is detected in that corresponding phase, and the impedance L and C will come in parallel, and the effective impedance will be appearing in the stator side of DFIG. The single line diagram of the grid connected DFIG with FCL DVR impedance method is also shown for the 575 volt DFIG. The switching strategy for FCL DVR impedance. In the first case, there are 5 different cases. In the first case, DVR is working in the normal operating mode with no voltage sag. Hence, DVR and FCL DVR will be bypassed. Whereas in the case of symmetrical partial voltage dip or unsymmetrical partial voltage dip conditions, the FCL crowbars will be deactivated and the DVR's mode will be activated in order to assure a partial voltage restoration. If there is a severe unsymmetrical fault which causes an overcurrent in the rotor, then the FCL DVR impedance crowbars of those phases which has overcurrent and severe voltage dip will be activated, while as DVR inverters for those phases will be deactivated. And a severe symmetrical fault condition, all the three phases of FCL DVR impedance crowbar switches will be activated and DVR pulses will be deactivated. So this is implemented in the control strategy of FCL DVR impedance and DVR method. In the DVR method, the rated three-phase voltages are compared with the reference values compared to the measured values in the alpha beta axis, and the error is controlled using PR controllers, and the output of PR controller is fed to the DVR inverter through an AND gate. During fault current identification, the switching strategy of the FCL DVR impedance will be checked for, and correspondingly turn off signal goes to the DVR pulses through the AND gate. So FCL DVR impedance parameter determination. The steps for determining the parameters of FCL DVR impedance is shown. Initially, we will be determining the safe limit of the fault current allowable at the stator side, and from this fault current, the equivalent impedance that should appear at the secondary side of the transformer will be calculated, and Z equivalent is given by omega 0 into L, because when L and C is in parallel, C will be a very high value. Capacitive impedance will be a very high value. And inverter filter parameters are next determined, and turns ratio of the series transformer K is also calculated. Then the same FCL DVR impedance DVR has to act as a partial voltage restorer in the DVR mode also. The capacitor voltage across the voltage across the capacitor is calculated, and based upon this value, the DC source value of the value of the energy storage system of the DVR is also determined. The parameters of FCL DVR impedance for DFIG determined is shown in the table. So the fault parameters that we have considered for analysis for the VOF is equal to 90% that we have considered earlier, VOF is equal to 80%, and also symmetrical fault condition with the P is equal to 0.8. So VOF is equal to 90%. This was the condition when the stator voltage of one phase was severely falling to zero, and the fault current in the stator is also represented. As a result of the FCL DVR impedance activation in the B and C phases, the voltages across these two phases are improved, and the improved stator voltage is shown in figure 46B. As a result of the FCL DVR impedance action, the VOF is now getting reduced to 8% from 90%, which is a very good result. And also the the stator flux trajectory, which was following an elliptical path, is now restored to the circular trajectory. The stator current after FCL DVR impedance action and the electromagnetic torque regulated after FCL DVR impedance is shown. We can see there is a slight rise in the stator current during the transient, during the fault clearance period. This is because the inductor current is still flowing through the SCR pulses takes time for switching off, and the inductor currents are still discharging. The harmonics component is getting reduced from 0.48 to 0.07 for VOF is equal to 90%, and the rotor current is regulated in steady state to 1 per unit value, but in the fault clearance period, similar to the stator current, there is a slight rise in the rotor current. So as VOF is equal to 90% is considered for FCL DVR impedance control method, the harmonics component is reduced from 0.48 to 0.07. The rotor natural current is reduced to 0.55, and negative sequence rotor force current is reduced to 0.11. So coming to the next case of VOF is equal to 80%, the stator voltage as a result of the stator voltage as well as stator voltage has a dip in the B and C phases, and the FCL DVR impedance when activated in the B and C phases, the stator voltage gets improved as shown in figure 54A, and the VOF is reduced from 80% to 26.3%. The stator current regulated as a result of FCL DVR impedance action is also shown. The rotor current regulation is also showing much reduction in the harmonics in the rotor current. Harmonics is getting reduced from 0.51 to 0.2. So in order to, so the steady state current, overcurrent is getting well reduced by the FCL DVR impedance method, but there is a slight rise in the fault clearance period, the rotor current, which has to be reduced, which we are proposing to reduce using a virtual stator flux damping strategy. In the virtual stator flux damping strategy, the natural component of the stator flux is opposed with the virtual component, and thus the stator flux natural component is reduced. And this is applied to the rotor reference current in the RSC control. So total stator flux now becomes natural stator flux plus forced component plus virtual component, where psi v is equal to minus of psi Sn. So psi v is determined in terms of the positive constants k1 dash and k2 dash, and the rotor reference current in terms of psi v is calculated as in equation 55. So based on the equation 55, with the help of K1 and K2 positive constants and stator and rotor currents in the D and Q axis, the D and Q axis rotor current references are determined. The optimum values of K1 and K2 are calculated with the help of two conditions to be satisfied. One is the rotor current reference should always be less than or equal to 1 per unit, given by the condition 56. And also the transient flux decay takes place 1 plus K1 K2 by 1 plus K2 minus K1 K2 times faster by the virtual flux damping method. So based upon these two conditions, the optimum value of K1 and K2 are determined. And as a result of the virtual flux damped FCL DVR impedance method, for a symmetrical fault condition, the rotor current rise during the fault clearance period is reduced with a faster decay as represented by figure 60b. And in the rotor current during VOF is equal to 90% is also reduced from 1.7 to 1.25. And as well as the C phase is also getting reduced to 1 per unit with a faster decay. VOF is equal to 80% had a rotor current rise during the fault initiation as well as the fault clearance period. These two periods also, the virtual flux damping strategy is applied, and we can see that there is significant reduction in the transient as well as both the transient periods of fault initiation and fault clearance by the proposed method. So transient flux method in case 1 reduces the transient rotor current to 1.25 at the fastest settling time of 22 milliseconds. In case 2, the settling time is reduced to 3 milliseconds, and symmetrical fault it is reduced to 10 milliseconds. So as a objective of our research, the three methods that we have suggested, that is PSDVR and virtual impedance method, PSDVR and dual controlled RSC, and virtual flux damped FCL DVR impedance method are compared with each other for the same DFIG parameters and same DVR with the 25% compensation. And we can see that the steady state rotor current reduction, rotor natural current reduction, harmonics component reduction are well accomplished by the virtual flux damped FCL DVR impedance method, whereas the series transformer rating is increasing from 0.13 to 0.52. So the proposed method of virtual flux damped FCL DVR impedance is compared with the existing topologies of switch type fault current limiter, series dynamic resistor, and inductive FCL coordinated DVR methods. We can see that the transient component reduction is well accomplished by our proposed method. Settling time is also faster, and steady state rotor current is also well regulated. And the negative sequence stator voltage component and VUF reduction is also possible. So as a conclusion of this phase, compared to the previous methods of fault current reduction that we have suggested as part of our research, the FCL DVR impedance and virtual stator flux damped method is getting finer results for symmetrical and asymmetrical fault current reduction, with stator side impedance and stator voltage improved. And transient flux reduction of FCL DVR impedance method reduces the transient overcurrent conditions only also. These are the publications of this phase. So as contribution of our research, 4 novel topologies of FCL DVR methods were suggested. In the initial phase, the PSDVR method of stator voltage control was suggested. Its limitations were tried to overcome with the rotor virtual impedance method. And during unsymmetrical fault conditions, the harmonics component reduction was tried to be achieved using dual controlled RSC and PSDVR method. And as a chief contribution of our research, we can see the virtual flux damped FCL DVR impedance method can be a promising solution for severe LVRT occurring in the DFIG. So conclusions of our research, the research on modifying the control of a DVR as an overcurrent limiter by avoiding any resistive elements such as crowbars or STBRs and keeping the RSC operation intact is studied. And the proposed method of FCL DVR impedance with the virtual damping flux strategy ensures voltage restoration in DVR during partial dips and overcurrent reduction during severe voltage dip conditions. As a future scope, High voltage ride through or HVRT requirement is a developing area for DFIG and also have been made mandatory by some of the grid codes. So the influence of the proposed methods on the HVRT has to be extensively studied. And the variable FCL-DVR impedance insertion with the semiconductor switches can also enable better control of the stator voltage as well as stator current. These are the publications. Acknowledgement. References. Thank you.
Ashok sir.
What I suggest, being the open defense, I request the research scholars and other faculty members to ask clarifications or queries. Research scholars and other faculty members can ask some clarifications or questions to the presenter.
Yes, all faculty members and research scholars may interact.
Now, why nobody is interested in this topic? Is it like that? There are many power system people, and this topic is of very useful. I don't know why research scholars in power system they are not interacting with the scholar. Nobody wants. It's wonderful. Anyway, the other examiners are there. They can please.
How the reviewers' concerns are addressed in your reviewers' thesis. Are there any comments? Have you received any comments from the reviewers and how those comments are addressed, if any?
Sheena, your mic is mute. Sheena, your mic is mute.
Shafi sir is telling something, I think. Shafi sir?
Your mic is mute. I think I didn't hear anything. Sheena? Sir, am I audible?
Yes, 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 sir. Yes.
Sir, am I audible now?
Yes, yes.
Yes, yes.
Sorry, sir, I removed this. Sir, the reviewer comments were addressed and they were included in the thesis and submitted, and the corresponding answers also here, sir. 3 reviewers were there. Clarifications I have on the PPT, sir.
So can you read out the salient features over the audience?
Sir, which question, sir?
Salient questions.
You mean the important questions?
Yes.
The first reviewer has given 21 questions, sir. I should read all of them?
Only
relevant, only few relevant questions.
Relevant ones, okay. So there was a thesis. In the thesis, there was a stator flux trajectory which was dropping to 0.2 per unit. So it was asked what is like to enlarge it and show it inside the thesis, and also the magnitude, which I have included. Then
I think you can put in presentation mode, I think.
oh, okay, sir. By inserting crowbar, can we control the torque? Is it useful in FRT? By inserting crowbar, the control of RSC is lost, and we cannot control the torque anymore. But being the cheapest method, it is being practically, it's even practically implemented for FRT in many wind farms. Have you done any study with the power flow from stator as well as from rotor to grid? Our study is basically for this, super synchronous mode of operation. So it has power flow from stator as well as rotor to the grid. The control strategy minimize.
How we have set the initial conditions?
Sir,
How we have set the initial conditions?
how I have set the initial conditions?
Yes, yes.
Sir, the stator voltage is set to 575 volts, sir. Stator voltage is set to 575, and the corresponding rated current is the initial condition without fault.
No, I am
And-
not asking. I am not asking that one.
How you
Anyway.
set the initial conditions? How you set the initial condition? How you set the initial conditions? That is the question.
Yes.
Sir, the initial conditions of the machine is working in normal mode is what I have considered, sir, initially.
And how this algorithm is useful over here, PSO that you have applied?
So the PSO algorithm is used for the tuning of the PR controller, sir, proportional resonant controller that we have used.
How we have applied that one?
Sir, I have used MATLAB simulation. So there is we can we can use both the Simulink model as well as the MATLAB code. So the PSO code was put into the Simulink model of the PR controller with the plant, and the step response was taken, and the optimal values were taken for the KP and KR of the PR controllers.
What was the objective function there?
To minimize the integral of square error, and also the maximum peak overshoot of the error. This minimization and this bird step 100.
Okay, next questions.
So the reviewer 2 has asked the cost considerations of the fault current limiters. So this fault current limiting is a developing area of research in LVRT. And as far as the LVRT system is concerned, the research is going on in FCL, and there are several methods which are available in the literature survey. So as a rough method, we can say the non-controlled type of fault current limiters are the cheapest, including the crowbar, passive crowbar methods, and superconductor-based fault current limiters are the costliest. So I have mentioned the VUF can reach a maximum of 50% single line to ground fault and a maximum of 100% during double line fault. So it was asked to give a value. I have included that value as a representation in the thesis. And also we have discussed a VUF equal to 50% in our results shown. Then 60, this is applicable to 50 hertz or not was asked by a reviewer. That is, this is we have done in 60 hertz. So is this applicable to 50 hertz? That is the Indian grid. Yes, this is applicable to 50 hertz also. Since the initial works were carried out in 60 hertz, I didn't switch to 50 hertz again for the easiness of comparison between existing topologies. As we change to 50 hertz, the corresponding results are shown, and this is included in the thesis. The harmonics component still remains the 11th order harmonics for 50 hertz condition. And
Here, hello, go back. This DC link voltage, please go back. Here, go back.
I'm going back.
No, not to
You're saying the waveforms?
go forward. Yes, waveform. 8.4 or something like that figure. 8.5. Yes, here. Yes, this figure. This DC link voltage, it is fluctuating.
So this is the fault condition, sir. LLG fault being applied. This is only the fault condition. Stator voltage dip, rotor currents, corresponding harmonics, and the fluctuations in the DC link voltage. Before the application of FCL DVR impedance method. So after the application of FCL DVR impedance method, the stator voltage is now improved like this for the 50 hertz, and stator current regulated, and the rotor current regulated, and the DC link voltage is now without ripples for 50 hertz. It was asked by reviewer, so it's 50 hertz, and the harmonics component is also getting reduced.
It is reduced, but not totally regulated.
Sir, in the case of negative sequence control, we cannot completely eliminate or make it to zero. That is what the studies have shown. We can regulate it or minimize it, but some amount will still remain. So that is why, whatever methods we have applied, there will be some amount of harmonics component being shown.
So you cannot say it is properly regulated. That is the concern here.
Sir, in all the reference papers also, they say like this, that negative sequence, it is very difficult to control compared to the positive sequence component.
How have you chosen those parameters? Go back. These parameters, how you have chosen?
So this is the 575 FCL DVR impedance parameters determined from the equations, sir. I have shown in the presentation certain steps.
Filter inductance, capacitance, all these values.
Yes, these are determined from this equation, sir. These are determined for the 50 hertz 575 volt DFIG. I have determined the values and applied. For the DVR, FCL DVR impedance parameters is this, sir. So as the parameters are varying, as the frequency is varying, or the voltage is varying, or the power is varying, correspondingly the parameters we have to redetermine, sir.
Anyway, go ahead.
Okay, I think other.
So there's still more. Shall I show it, sir? Or?
Just you show the salient points only. And I think all this has been incorporated in the thesis, no?
Yes, sir. Yes, sir. Yes, it is incorporated and submitted, sir.
And I think your DSC committee has accepted this particular revised version.
Sir?
DSC committee, or
DC
DRC committee, whoever it is there in your institute, I think they have approved.
Yes, sir. Yes, sir. My guide has approved the corrections, and after that only we have submitted the thesis.
Okay. Okay, and it is done from my side.
Thank you, sir.
Sheena?
Sir?
Okay. So congratulations. You have done very exhaustive work on your research topic.
Thank you, sir.
And congratulations to your research supervisors also.
Thank you, sir.
Then one question actually I want to ask is which tool you have used, but it's already asked by the Vivekananda sir. And did you conduct any error analysis? How will you predict the accuracy of your model?
No, sir. As an error analysis, it was not. Some schemes were developed in MATLAB.
Okay.
And existing, no, error analysis as such we have not done, sir.
Okay. Do you find any the percentage error between your values and your literature values? Did you calculate?
No, no, sir.
Okay. Okay. And can you see from the application point of view, your deliverables with the application point of view, how it would be matched
Sir,
or how you
sir,
can incorporate?
yes, yes, sir. Sir, from the application point of view, that is, I have done an industrial visit to the Kinfra wind farm, Kinfra-based wind farm at Kanyikode. There, they are using, there's 2 megawatt wind turbine. It is the latest aerofoil design and everything, and there they are using the crowbar technology only. DC chopper-based crowbar technology, which is the cheapest one. So as for now, DVR is not been installed as an LBRT solution for any wind farms. Rather, it is applied for some very sensitive loads, such as textile industries, yarn industries, semiconductor industries, etc. Because in the inherent mode, the DVR is capable of partial voltage restoration only. But as we are improving its possibilities, exploiting further possibilities of fault current reduction also with the same DVR, without the addition of any additional external hardware components, only with six anti-parallel switches. This is actually going to be a greater contribution to those countries who are having a greater contribution from their wind farms as the major power, such as Denmark, Ireland, Portugal, etc. The total contribution of the wind power to the consumption, total consumption is more. So for such countries, LVRT is a mandatory requirement now. Slowly, HVRT is also becoming a requirement. So DVR can be applied to HVRT also. Even our proposed method can be applied. In the near future, this is going to be a single DVR when considered can be modified to FCL DVR impedance method and can be applied to existing wind farms also. But the cost has to be cost consideration has to be studied.
Okay, okay. And I forgot to mention one thing. Your presentation was excellent. Okay, it's very nice presentation.
Thank you, sir.
And your slides are also very fantastic.
Thank you, sir.
And only one drawback that I've noticed is your initial work has been published in some waste journals. Okay, that I can't tolerate with those things. But later on, you identified the importance of your work and you have tried to
Yes,
communicate your work in the Hiller and Francis
yes, yes.
journals. It's
Yes.
very good. It's appreciable. But try to avoid all these mistakes. Okay, maybe you may not be knowing much regarding the quality of your work. Okay, anyway. Uh, so thank you very much. Your presentation was very nice, and you limit your presentation within the stipulated period. Even though it was not instructed, you should limit your presentation within 40 minutes, but it is covered within 40 minutes. I wish you all the best. Good luck.
Thank you, sir. Thank you so much, sir.
Ms. Sheena, shall I have some clarifications?
Yes, sir. Yes, sir.
Yeah. You talk about this in your presentation about the severe voltage dips. Okay.
Yes, sir.
What is the definition of severe voltage dips? How do you define the severe voltage dips?
Sir, for that, the definition of partial voltage dip. That is, partial voltage dip is a condition where there is a voltage dip and there can be negative sequence components or harmonics components present in the rotor current, but it will not be that high enough to saturate the RC. That is, RC control can still be sustained without doing much damage to the RC. So that is the definition for partial voltage dip conditions. So usually for symmetrical fault conditions, for P less than or equal to 0.4 is considered as a partial voltage dip. So conditions where the current is too much, that the natural component or the harmonics component of the rotor current is so high that the RC will eventually reach to its saturation condition, losing its control and resulting in the tripping of RC or damage of RC. That is considered as a severe voltage dip condition.
Is it as per IEC? This is not the definition as per IEC.
Sir, this is a definition I got from the textbook.
Yeah, this is okay to an extent. Okay, this may be the result of those things. Okay, as a research scholar, probably you can look into IEC definitions also. Okay, because it's a power quality issue. So you can look into basically this. You told partial as well as severe. So the relevant IEC. Similarly, about the severe symmetrical and the symmetrical faults also, because these are qualitative statements. A research scholar is always advised to give quantitative statements. Okay, instead of giving higher, good, like that, or severe, something like that. Always you, of course, in our daily life, you used to tell qualitative statements only. That is why things are coming like that. But it will be always better for a research scholar to talk quantitative statements. That is one thing. What are the DFIG? You told it is 1.5 megawatt
Yes,
DFIG.
sir. Yes, sir.
There are the simulation parameters of DFIG. You have not shown clearly.
Sir, shall I take it once more, sir?
Just tell me what are the simulation parameters you have used, because you have used MATLAB.
Yes, sir.
Right. In MATLAB, there is a default DFIG.
Okay,
Okay,
sir.
there is a model already available.
Yes,
Okay, but that model, if you use, you may end up with a wrong result. Okay,
Okay, sir.
so you may have to use the DFIG parameter simulation using your DFIG parameters.
Yes, sir.
Yeah.
Sir, I have used that fundamental equations of stator voltage and rotor voltage, which I have initially shown. That was transformed to DQ axis.
Okay.
And from that DQ axis, the RC controls references were developed.
I
Flux equations.
understood, and that is the way also. But
Yes,
I am asking about the parameters in the simulation platform.
Sir, we can give, it is in Simulink, sir, so we can give the voltage is 575 volt. It is a the voltage which is usually followed in Central Europe, Canada, etc. is 575 volt line to line when it is industrial.
That I agree. That is 20 kV, 575 and all these things. It's okay. I am asking about the simulation parameters. Have you used the Simulink model? What is existing in the MATLAB, or the Simulink parameters you have changed it? That is what I am asking.
The parameter values, sir.
Yeah.
So parameter values I have changed. For 50 hertz for that condition I have changed. The slip value I have changed.
Anyway, you look into that. Okay.
Okay, sir.
Why I am telling that simulation there are so many simulation parameters in the default model of MATLAB.
Yes. Yes, sir. Yes, sir.
Normally, for MTech students, they whatever be the case, they just simulate and finally ending up with mistakes.
Yes,
Okay.
sir.
So you
sir,
have
sir, one thing, sir. Sir, in MTech, I developed a DFIG model in SQL, which was developed by CDAC. So I had an idea about how that was long back, but I had an idea about the equations and how to do that.
But because here you told Simulink.
Yes, sir. Yes, sir.
Yeah, Simulink, that much flexibility is not there.
Yes.
They have to take the default and then change it. They change the parameters.
Okay.
So that is what normally. Okay, just look into that.
Yes, sir.
You told about the faults. You have applied the faults and you have taken the waveform. Correct now?
Yes, sir. Yes, sir.
Where you have applied the faults?
Sir, for the BUF is equal to 90%, a double line to ground fault was applied at the high voltage side of the transformer.
Terminal faults? You mean terminal faults?
Not near the stator, sir. In the step up transformer, near the step up transformer, high voltage side.
My question is,
yes.
is there any impact? Is there any impact on the location of?
Yes, sir. There is impact. There is impact, sir. Like if your location, the fault impedance, and the type of fault. These three parameters are very important.
Type of fault, it has come in your presentation. You told
yes.
Yes.
Yeah, location I have not specifically mentioned, sir. Yes,
yeah, at least something should be there about that location, because it is also depending on the location of the fault.
Yes.
So, because everybody knows that.
Yes.
You told that your method is better than the supercapacitor or other methods like that. Definitely, I agree. Okay. Then the reactive power requirements. How actually it is met in your case, conceptually. Okay, you can have all this waveform and all these things are there, but we all know that there will be reactive power requirement comes. In this capacitor method and all these things, capacitor energy is released. Am I correct?
Sir, you're talking about the DFIG or the FCL methods that we have proposed?
You have used, see, basically LVRT when the fault comes, okay,
Yes,
for
yes.
compensation, okay, these many methods you have compared, supercapacitor methods and all these things. Nah?
Yes, sir.
So the advantage of those methods are the reactive power energy stored in those mechanisms are least, and the stability or the whatever it is achieved so fast. But in your method, how the reactive power is basically compensated? Or
Sir,
have you
we,
thought about that?
uh,
Or
no, sir. Actually, I have done the stator voltage restoration through which the necessary react. See, the DFIG in its supersynchronous mode of operation is itself supplying a reactive power from the stator. Active and reactive power from the stator, sir. So, as far as DFIG is sustained in its operation, there is a reactive power supply. Otherwise, the study it's not done, sir.
I understand what you are telling, but you may have to look into that.
Yes,
Okay.
yes, sir. Yes, sir.
The
Yes,
super synchronous modes, it may release, but just look into that.
Okay,
What
sir.
is the percentage and all this thing, because it is your thesis. Your
Okay.
thesis should be a foolproof thesis.
Okay, sir.
Right
Okay.
now. And similarly, you told about 11th order harmonics.
Yes, sir.
Okay. Do you think that only 11th order harmonics is there always?
No, sir. No, sir. We have taken at a particular case consideration.
Yeah.
In subsynchronous mode, it is not 11th order harmonics. It is majorly coming as 9th order.
Not
And
only
in the super synchronous also, we have 21, etc. coming.
Yes.
Yes, sir. It's coming. But as a case study, like this is having more ripples and
I agree. But there are other
yeah, other yes, other harmonics also,
I
sir.
have shown a slide of these are the harmonics out of which I am concentrating on, or this study concentrate on 11th harmonics, something like that.
Okay, sir.
Okay. Naturally, other harmonics, when you are talking about, say, when you are studying or when you are analyzing or when you are controlling for this particular, there can be impact on other harmonics.
Yes, sir. Yes, sir.
Sometimes other harmonics may reduce, sometimes other some other components may increase also.
Yes, sir.
So these are negative sequence is coming. Yeah.
Yes,
So
yes, sir.
that is the reason. Negative sequence coming, so we have to be extremely careful.
Okay, sir.
Some of your reference paper, if you look at, you can see that.
Yes, sir.
I've seen the reference paper you have sent. Okay.
Okay.
Then what could be the reason for peak ripples in some of your waveforms? Have you noticed the peak ripples in your virtual impedance method? Peak ripples. Peak ripples. There is a problem actually that is called peak ripples. Okay, you can look into that.
Okay, okay.
Peak ripples is a basic problem. That is during the peak, there will be ripples. Okay,
Okay.
of a particular maybe constant frequency. Okay, it is basically because of the power electronics components. Okay, that peak ripples is coming. That you can look into that.
Okay.
Then you talk something on optimization. What is that optimization?
So that PR controller gain values
What
optimization.
is that?
So the KP and KR values that we should supply for the PR controller was optimized using PSO algorithm.
Yes, algorithm. Okay.
Yes.
Okay, that is what. Okay, because you told something about optimization, so I could not understand what you have optimized. Okay, so it is control parameters, KP.
Yes, KP, KR parameters.
Yeah, parameters. Okay, what is the which parameter is suppressed to get this optimum?
So the integral of error square, minimizing the integral of error square function, and also minimize the maximum peak overshoot of the error. These two were considered, sir.
Minimizing the integral of error square. Okay, and basically it is the sum of squares. Correct?
Yes,
Yeah?
yes, sir.
Minimizing
Integral of
sum of squares
its integral minimization.
And integral means sum of yeah.
And the maximum peak overshoot minimization, sir, of the error.
Okay.
Steady state error.
Overshoot of the steady state error. Okay. Okay, I may have to look into that. Okay, fine. Why there is a dip in the electromagnetic torque? Is it because of dip in the current? In some of the slides I have noticed there is a dip in the electromagnetic torque.
So
Is it-
during fault condition, the power naturally goes to zero, sir. So of DFIG.
when it is clearing the fault, when the fault is getting cleared,
Oh,
that time why I don't know. Everything has come to the normal state, immediately a dip and then come again normal. I have noticed in 1 or 2 slides, I don't know exactly that. I would appreciate much better way if you have done some stability studies also along with this. Okay, otherwise also it is okay. Everything is okay, but it will be better if you, as a power system engineer, being a power system engineer, okay, who are doing this wind or solar, stability at the end will be always better. Okay, what is the
Okay.
impact on the grid? Okay,
Okay.
so it's a very good study. Deep coverage is there. Okay,
Thank
and as Dean told that your presentation is very nice. Okay, okay, Xavier sir.
Okay, thank you, sir. Thank you.
Thank
I
you.
think there are, is there any other queries or suggestions from other faculty members and researchers?
Actually, Dean Research has raised a hand.
Yeah. Okay, okay. I think
Suresh Babu, sir.
Suresh Babu, sir. No, I think I could not do anything. I think Suresh Babu, sir. No, I could not. I think I could not. Okay. Okay, I think any other comments from other faculty members? Ashok sir, I think there are no comments, I think, other.
Then in that case, we may conclude.
Sir,
Yeah.
the procedure is like this. The respected chairman has to declare whether the candidate has successfully defended her thesis and whether we can recommend this work for awarding PhD degree of University of Kerala.
Yeah. Okay. So the research scholar, Ms. Sheena, has presented the work done during the thesis time and incorporated all the queries and clarifications raised by the examiners in the thesis, and also clarified all the questions asked by the examiners as well as the audience during the presentation, and in a satisfactory way. And so therefore the board of examiners appointed by the university recommends the award of PhD degree to Ms. Sheena Latif in the Faculty of Engineering of the university. So on approval of the university, so Sheena will become the Dr. Sheena. So congratulations to the research scholar, Dr. Sheena, as well as Gate Professor Xavier.
Okay, thank you, sir. Thank you, sir. Thank you very much. Thank you. Okay, okay, Sheena.
Okay, so on behalf of the University of Kerala, I congratulate Dr. Sheena Latif and Dr. Xavier sir, and also respected chairman for sharing your valuable time with us. Thank you so much, sir, and you have given a lot of valuable comments to the scholar. It's like a teacher taking class.
Thank you, sir.
Very interesting.
Thank you, sir. Yeah, yeah. I have actually noted down all the comments of Ashok sir. Actually, there is also we also got some insights from the queries of the Ashok sir from the Department of Electrical Engineering. I thank Ashok sir as well as Dean of Faculty of Engineering and Technology, Shafi sir, and Principal, and all other faculty members and researchers who attended this defense. Thank you all. Thanks.
Thank you, sir. Thank you so much.
Yeah. Okay, thank you all.
Thank you.
Thank you very much. Thank you all.